So mathematicians decided that they really only like real number denominators. If they're going to be dividing something into equal parts, they think it shouldn't be so complex as this. So for that reason, they came up with the process of making the denominator a real number. And so far, the best process is by multiplying by the conjugate. It'll probably never change because people generally agree that it's an okay process. Don't want an imaginary denominator? Okay, well, multiply top and bottom by the conjugate, which is the exact expression, but you just change the sign of the imaginary part. If you do it right, you'll have a real number to divide by. So you're going to FOIL the top, do double distribution, distribute the 3 and distribute the I. And you'll do that again to the denominator. Distribute the 4 and distribute the 2. So you can pause, check your signs, check your numbers, check your exponents. Let me know if you have any questions. So you now know that I squared can be simplified to -1. So do that. The two terms in the middle cancel, which is why we're using the conjugate, because it'll cancel in the middle. Two negatives make a positive. Combine like terms. Here you've done great. You've shown all this work. You're showing you understand what you're supposed to do. It just says simplify. Well, I told you to use the conjugate. Most fractions wouldn't. Using the conjugate correctly, you get here, you're almost at 100% full credit. Your fractions have to be in simplest fraction form. So they all 3 divide by 10. Well, I guess I'll just put a 9 there. All over 2. This is full credit. Or it'll often look like 2 separate fractions. 1 over 2 minus I over 2, or actually it'll look like 1/2 with I in the middle. So both of these are full credit. And now we're thinking of 2 equal parts, which is much simpler than how the equation started or the fraction started. It took a lot of work to get there, but the result, it's nice. 1/2 minus 1/2 I. It's a lot more usable than this. Somehow it's the same. This is completely equivalent to this. Okay, go ahead and try number 2. A weird number that is 61 involved. 61. You wrote 30. Maybe did you write 36 or? So, 10 divided by 10 will leave a 1 right here.
Is it right if I just switch sides?
I think so. Let me do it real quick and then you'll know for sure. Number 2 conjugate. Oh, we don't like this denominator. Let's rewrite it. Let's do algebra to rewrite it. And it'll be more useful. I got 16 minus 7i over 61. Random numbers. If you wanted to write it as 2 separate fractions, that's how it would look. This is full credit. Who's got a question on number 2? Okay, if there aren't any questions, just finish it up. Get out your homework from yesterday, page 52. I can do a couple of those problems. Alright, so here's we're working odds. Here's 1 through 21 odd. Does anybody ever request? I'd like to see one of these worked out. Not sure where the answer came from. Not sure why you were wrong. We're not doing anything new today, so this is your last chance to get this done and do something new Monday. Alex? I got confused. 19? Which one were you going to say? Okay, so 5, what's important about 5 are these parentheses. So if there's parentheses and the exponent on the outside, everything in the parentheses gets squared. So this will be 7 squared and I squared. 49i squared times 6i. And we're practicing I squared becoming -1. So we got -49 times 6i. 50 times 6, 300, -294i. 19, we'll use the conjugate. Okay, so there's not a full FOIL on this one, not like a double distribution, you just distribute the 2. But down below you do have to do double distribution. And we got a 64 here. Alec, what do you think so far? Okay, and you can see here the textbook's learning it. Either or. Okay, other requests.
So you don't just add them, you multiply them? Now you just add them. I thought you added them to 7 minus 8i and then 2. So make 9 plus 8i.
Oh, you just gonna multiply. Yeah. Distribute. Distribute. You got a question? Somebody else have a question? Yes. Yeah, let's scroll to 33. On 33, you're intrigued at J, just like in Y, like so. The sector of electricity, industry of electricity, and the mathematicians they didn't talk and agree that everything's I. So in electricity, instead of using the imaginary I, they call it J. Think about this ohms, so unit of energy. So the formula calls for multiplying the currents and the impedance. So it's like voltage would be 3 minus J amps times 3 plus 2J ohms. And it's interesting that they're giving you, this units and things when you haven't even learned about ohms and amps in electricity. But this problem is in the, electrical engineering textbook, and then you learn about the voltage and the amps and the ohms. And here you're just learning, your skills of multiplying, so you're ready to learn those engineering concepts. So anyway, we're foiling. So it's 9 minus 2. We're going to take the j squared out and make it -1, just like I. 9 plus 2. Let's multiply something on here. So 3. Mark?
What about the n and the l then? I didn't get anything after 21. Because it just started putting in like n's and l's and n squared.
Okay, yeah, let's do 23. Let's do 23. I really have not spent any class time on problems like 23. Like, we read it on Monday in the textbook, and I have not spent any time on it. So let's look at 23 right now. So 23 is different from all of the first half of the problems, and then the actual equation. There's an equal sign. So we're going beyond simplifying to solving. And so we'll just put a line in here. Our goal is to find what m is, to isolate the variable, solve the equation. So we'll subtract 10 from both sides. Get 2m squared is -10. Divide. And get m squared is -5. So far, so good. And then your last step is to solve by square rooting. Square root, square root. And we get m is, whenever you solve by square rooting, you use a plus or minus I square root 5. Question about the plus or minus sign?
Why do you have to put the on?
Well, I could have shown my work. I could have said m is plus or minus the square root of -5. And we don't leave a negative, so we put it out front.
Change the 27.
Yeah. Alright, now we got a 3/4 in front. I'll subtract 12 from both sides. What's our best method of getting a fraction away from a variable like this? We don't like to multiply or divide fractions. What do we do? Get rid of this thing? Go ahead. Yes, multiply by 4. You can actually do 4/3 in the same step. It's a little shorter. So I'll multiply by the reciprocal on both sides. X squared would be negative 48/3. 12 times 4/3, 12 times 4, 48. 1 times 3, 3. 48 does divide by 3, so x squared is negative 16.
Would be x equals negative 4 or 4i.
Yeah, so x is plus or minus the square root of negative 16. X
Wait,
is I squared 4.
why would you just put 4i?
Oh, you're right. Square root of 16, that's a perfect square. Get rid of your radical y. 4.
Would it still be plus or minus?
Yep. Plus or minus. Well, we're actually going to spend more time solving by square rooting in future chapters. So in the future, I'd say I'm only going to give you half credit. But on this problem, so I like to look at like how many steps were involved. If this was a 5-point question and you correctly isolated your variable and you correctly square rooted and you correctly took an I out, the I is the most important part, to be honest with you, but you forgot the plus or minus, they'll take 1 point off. Okay, when you're looking at, it says find the values of L and M that make the equation true. So you want to just make this side look like this side. Okay, so like this is the imaginary part, and this is the imaginary part on the left and right. So ignore the equation. Just look at how this is 3m, but this is 27. What does m have to be for this to look like this? M equals 9, because there should be a 27 right there.
Would L be 18?
So it looks like. So matching the left to the right, you can just say, so technically this is called the real portion, and negative 12 is the real portion, and then this part with the I is the imaginary. And this part's the imaginary. So you set the real part equal to the real part, and the imaginary part equal to the imaginary part and solve. So I'm going to say 6 minus L is negative 12, and 3m is 27, and you just solve both of those, like kind of like coefficients, or both of those terms. Positive 18. Negative L equals negative 18, so L is 18. Oh, the answer was up there. And then M is 3. I'm sorry, 9. Divide by 3 is 9. These are usually bonus questions on the test. I find that it's more appropriate in the curriculum as a bonus question. So if this is supposed to be 3 here, this must be negative 4. And if this is supposed to be -6, then this would just be 1. Other questions? Okay, so we're not doing anything new. I'm not going to add to this today. I'm going to let you practice this more, and then Monday I'm going to start a whole new section. But there was a lot of discussion in other classes about the importance of this I and these complex numbers and why we're learning it. And so we talked about engineering a little bit, and I found out that a lot of our students, a lot of you guys are interested in going into the health field. Not necessarily like science or engineering, but really towards the health and human services field. So anyway, based on conversations I had with other students, I started looking into the biomedical field. And so we're going to watch a short video on types of engineering, actually, because engineering, a good portion of the curriculum works with these complex numbers, kind of like this electricity problem we just did. But I wanted to show you all of the schools in Florida that offer degrees in biomedical engineering. These are just the first ones that come up in Google. UCF has a degree. You can get a minor in it, you can get a bachelor's in it, you can get a master's in biomedical engineering. And based on the classes we offer here, and being in honors algebra 2, you guys like totally have that option for your future, like if you want to work for it. So like, have you guys spent time looking at college websites and looking at different degree options and what they look like? So this is UCF, and this is their Master of Science in Biomedical Engineering. Talks about what it does, and we're gonna watch a video on what biomedical engineers do. But I do encourage you to start looking at like different careers in math and science since you're on this college prep course, right? Like, so the conversation came from like, why are we having to learn this, Mrs. Baldwin? And the answer was, you're in a college prep class. Like, enrolling in this class means that you intend to go to college. And the reason colleges want you to know this is because it's important for certain curriculum. Like, here is a biomedical engineering program at a school, and this is one particular class. And so look at this learning outcome. Upon completion of this course, you want to manipulate and perform algebraic computations with complex numbers. The very first outcome you see here. And you're starting to learn about complex numbers right now in Algebra 2. It's not a reason to shy away from math. It's like, wow, I'm already starting to learn these things that are going to be useful in a real career. Long story short, here's your 10-minute video. Part of the curriculum is exploring careers and things, so that's what we're doing today. And then after this,
From imagining what it might be like to create our own city, to learning about the chemicals that go into our food, we've already covered a good amount of engineering history. Civil, mechanical, electrical, and chemical are the 4 main branches of engineering, but there are many others. Some have been around for centuries, while others have developed more recently and are rapidly growing. Some have even broken off of existing branches and are quickly becoming their own fields. One example of this is aerospace engineering, which handles the design and construction of air and spacecraft. This was a natural progression from mechanical engineering, as we started creating machines that could fly. Another example is environmental engineering, which uses engineering practices, soil science, biology, and chemistry to help find solutions to environmental problems. We'll cover these and others in more detail later on, but for now, let's focus on 2 of the more prominent disciplines of engineering, industrial and biomedical. After we learn about the history of these 2 branches, we're going to see what it would take to use both of these fields to build and design a fully functioning artificial limb. So stick around. Industrial engineering has been around as long as we've had factories and other engineering systems. Just as mechanical engineers work with a bunch of different parts to design a machine, industrial engineers work with many different elements to devise an efficient system. And it's not just the machines they have to think about. They also have to consider the workers, materials, energy flow and communication that are needed to provide the best product or service. Other branches of engineering often take apart each system and analyse all of its parts separately before putting a system together. But industrial engineers do things a bit differently. They look at the system as a whole first, and then move on to see how the different parts work together. Then they can focus on the specifics to achieve the best results. It's all about optimization, and one of the most important areas that industrial engineers try to optimize is the assembly line. It's where we can see the biggest improvements in quality, delivery time and cost. The drive to optimise the assembly line is why many factories have switched over to more automation instead of manual labour. And it's caused the idea of lights-out manufacturing to grow, which is where factories and manufacturing operations don't physically need humans there to run or operate. Some machines are far less concerned about needing light or heat and air conditioning for that matter. And they're much less likely to complain, but we're still a long way from a world where robots and machines run everything. Until then, we can learn a good deal from Frederick Winslow Taylor, an American engineer who we see as the father of industrial engineering and scientific management. Around 1881, Taylor introduced what we know as time study. He found that the efficiency in a shop or factory could be greatly improved by looking at the workers and eliminating as much wasted time as was reasonably possible. His work led to major improvements in factory production by focusing on one of the biggest variables, people. Taylor's teaching soon became widespread, with his work titled The Principles of Scientific Management being published in 1911. While industrial engineering might not be as flashy as some of the other professions, it's central to the overall function of the other branches. It's the backbone of our engineering skeleton. It's been in the background of engineering ever since we built the first factories, which brings us to one of the new fields of engineering, biomedical. It's often used synonymously with bioengineering, but the two are not exactly the same. Biomedical engineering applies engineering skills and principles to biology and medicine, usually for the purpose of healthcare. It focuses on human and animal biology, whereas bioengineering is typically used as a broader term that can include other biological systems, like plants. Biomedical engineering focuses on advancements that improve our health, from diagnosis and analysis of medical conditions to their treatment and recovery. This is where we'll learn the skills to try and make an artificial limb. Biomedical engineers differ a bit from the other disciplines in that they often need to apply modern biological principles to their designs. For example, you have to make sure that the materials of an artificial organ don't cause an unwanted reaction inside the body, and that an artificial limb moves in similar ways to its organic counterpart. As such, biomedical engineers need to have a good working knowledge of many other fields in addition to biology, including mechanical and electrical engineering, material science, and chemistry, to name a few. And biomedical engineering shows up in most of our lives. Beyond artificial limbs and organs, we have it to thank for defibrillators, pacemakers, MRI and CT scans, and insulin pumps. It's striking to think that most of these technologies weren't around 50 or 100 years ago. That's because biomedical and bioengineering didn't really show up until after World War II. There were certainly biomedical inventions before that, but they were mostly left to the doctors and physicians. Some of the earliest evidence for the practice that we found has been a 3,000-year-old wooden and leather prosthetic toe found on an Egyptian mummy. Moving forward to about 200 years ago, the French physician René Laennec came up with an important biomedical invention, the stethoscope. After being appointed as a physician in the Necker Hospital in Paris in 1816, he developed the stethoscope in response to how uncomfortable it was to have to lay your ear on the person's chest to listen to their heart or lungs. People who enjoy their personal space have been thankful ever since. X-ray imaging was another early biomedical discovery. In 1895, German physicist Wilhelm Conrad Röntgen discovered X-rays while experimenting with electric current flow. He took the first X-ray photographs, which included the interiors of metal objects and the bones of his wife's hand. Even simple crutches and walking sticks can be looked at as early biomedical devices. There was a medical problem, and people used what they had available to them to improve their situation. But biomedical engineering didn't really take off until 1961, when the University of Pennsylvania offered the PhD program of biomedical electronic engineering, the first in the United States. Now that the field was more established, one of the biggest steps forward for biomedical engineering was computers. With computers, we can begin to analyze data much faster, which made it more efficient to evaluate patients and opened up new ways of doing so. Along with the invention of the internet, this is what's allowed doctors and physicians to create a worldwide network of data to find medical patterns and correlations. It also led to the new imaging opportunities like the MRI and CT scans, which began to pick up in the 1970s. Moving forward, advancements in medical instruments and electronics continue to be a major goal of biomedical engineers. They continue to seek the answers to questions like, how can we better take images of the body? Can we reduce any radiation involved? Can we come up with better analysis and measurement systems? How many tests can we do from a single drop of blood? But there are still some major challenges that biomedical engineers are wrestling with. One of them is biological modelling. We want to know how we can simulate the body and what's happening inside it. If we can get a realistic and reliable simulation, then we can use it to run experiments on rather than using a real person. It would allow us to both experiment in ways that could be harmful to a real person and also to repeat tests more than we normally could. Another area we'd like to learn more about is drug delivery. We want the medicine that we create to get where it needs to go. This is because certain medicine and treatments become less effective depending on where and how they're delivered. It's also important to know how the body will react to any implanted biomachines. This is where material science really comes in. One of the more interesting recent developments here is called cell encapsulation. This is where we surround the cell in biomaterials so that it's protected inside the body. The materials can act as barriers to protect a transplanted cell from being attacked by its host's immune system. The technology is somewhat new, but it has the potential to do wonders for cell-based therapy. Materials are also important as we develop prosthetics even further. When we're replacing something like a hip or a limb, there are many potential issues that we need to worry about. Some of these include making sure that bacteria and infections won't thrive on the material we've implanted, that the material is durable and will last a long time. Let's look at what it might take to replace a fully functional leg. There are many more factors at play than we'll go over now, but let's look at the big ones. To start off, the strength of materials is going to be pretty important. We need the mechanical bones of the leg to not only last, but to handle both the static and dynamic forces that a leg goes through. A material that handles the constant stress and strain of standing might not hold up well to the forces that happen when we run. Once that's figured out, we'll need to look into power and electrical engineering if we want it to move like one of our legs. This is also where programming and computer science might play a big role. Furthermore, it's not just the strong rigid materials that we'll have to worry about. For instance, our knees and many parts of our bodies contain cartilage, which act in part as shock absorbers. There are also fluids in our knees that help them move, called synovial fluids. Finding out how to replicate these, things like hyaluronic acid, could go a long way in recreating an artificial leg. Now, once we've figured out the design for the leg, we'll want to go back to our teachings about industrial engineering in order to make them in a factory. Not only will it be good to make them efficiently, but we'll also want to make sure they're made with the best possible quality. You see, we have the potential to do great things when we apply what we've learned. Like most engineering pursuits, things really come together when we combine at least a few of the different fields. So today we started off by learning about industrial engineering and the different factors involved in an industrial system. We talked about Frederick Winslow Taylor, the father of industrial engineering, and his work with scientific management. Then we moved on to biomedical engineering and bioengineering, along with their early inventions. Finally, we ended our lesson by talking about the future of the biomedical field and saw what it might be like to bring our teachings together in creating an artificial leg. Next time, we'll be moving on from our history-based lesson.
So you have an assignment in the textbook so that you can really finalize your complex number work. I'm going to turn on one light. You have the rest of the class to work on it. It's page 50. I'm going to do them too. I got through like probably 8 or 9 problems earlier. So. Okay, yeah, you guys should